Two rocket cars, each with a mass m, are connected by a tether. If each rocket car has a thrust F, what is the resulting angular acceleration? So I'd like to use Newton's second law for rotation as a starting point for this. In other words, tau equals I alpha. But I'd also like to use this simple example to kind of demonstrate, like, how do you find I for like basic systems? And the basic concept is that you're supposed to sum over mr squared, which in this case, since each of these rocket cars has a mass m, and this is set up symmetrically, so I'm going to assume that each rocket car is a distance r from the center of rotation. In other words, the center of rotation is right here in the middle, right? And r is defined to be the radial distance from that. So simply, I'm going to say it's going to be mr squared for the one rocket car plus mr squared for the other rocket car is equal to 2 mr squared. So that's how I find I, right? So that means I'm going to put in 2 mr squared alpha for that side. How do I find the total torque on this system? Well, the torque, there's kind of two of them, right? So I think I could say just tau 1 plus tau 2. And tau, like if I say, okay, maybe tau 1 represents the torque because of the thrust force F on this rocket car, right? And that force is applied a distance r, or with maybe a moment arm r, from the center of rotation. So I'm going to say rf for that one. Let's see, that one was up, the other one is down, so maybe the other one should be minus rf. Wait a minute, 0 torque? I mean, this should work, right? This thing should be accelerating a whole bunch the way it's pictured. Oh, you know what I screwed up? I had some linear thinking still left there, hold over from what we've been doing. And I got to think about this rotationally, right? Like this force of thrust on the right rocket car is an upward force, but it's accelerating the system rotationally in a counterclockwise direction. This is a downward force, but from a rotational perspective, it is also accelerating the system in a counterclockwise way. So it makes sense that both of those should actually be summative. In a very formal kind of way, you could use a right-hand rule and say, okay, point the fingers of your right hand to the right, turn them in the direction of the force, which would be up in this case. Thumb should point out of the page for that. And if you did the same thing for this one, you'd point your fingers of your right hand to the left, then curl your fingers down, and your thumb also points out of the page, which is the more formal mathematical way of convincing oneself that those two torques are indeed in the same direction. We're only interested here for this problem, I think it's going to suffice, that is, to know the overall magnitude of torque, and that is going to be 2RF. So that's what I'm going to put over here, 2RF, and lo and behold, the 2's cancel. I can cancel one factor of R, and I think that means that, whoops, I start to write already before I meant to. Alpha is going to be equal to the ratio of F over mr, which I believe is the same result we got for just a single rocket car that was connected to a tether that was sort of rigidly connected to the ground, and it was spinning around there. And that kind of makes sense, right? I mean, aren't these two rocket cars individually kind of doing that same thing? Like, really, for this rocket car here, does anything change that it's connected to another rocket car versus not just like, like there's some nail holding it down on the ground right here? Really, it doesn't make any difference, so it shouldn't be surprising that we got that same result.